That's why, like, when I was just, could we do a thing with this, and he's like, it would take like, for us to get the back in that order. I'm like, oh, right, it should absolutely just copy paste it, and we should not care about this specific thing, but I think we should.
Okay, good. Wow, that was the fastest setup ever. It's shocking.
Oh.
Maybe we're finally getting the hang of this. Maybe I can start saying something since we have like 1 or 2 minutes before. Yeah. Okay. So greetings, everybody. So before I introduce the speaker, as a reminder, we have a colloquium on Friday with Mihai Chu is coming to visit. And then there is a colloquium dinner afterwards. The seminar is paying, so I encourage you to come. And then we have Koi combinatorics lectures is also occurring. And we also have there is a conference dinner. Again, that's a freebie. So please join us. It should be a super fun weekend. What else? Next week is even more busy than this week. It's sort of shocking. But anyway, all right. So I am happy to introduce Steve Karp. So he's visiting for, I guess, until tomorrow, going back to Notre Dame. But what can I say about you? Let's see. You're a student of Lauren Williams, and you have been at Michigan. You had a postdoc, and you also had a postdoc at Université du Québec of Montréal, which is a very nice place to have a postdoc. Did you speak French? I guess you did. Oh, maybe not. A bit. Okay. So anyway, okay, I will not test. I'll test you later. So today, Steve is going to be talking about q-Whittaker functions, finite fields, and Jordan forms. Thank you. Watch out for the board.
Yeah. All right. Thanks very much for the lovely introduction and the invitation, and thanks everyone for coming. My slides are on my website, so if you Google me, you can find my slides and follow along. So I'm going to speak about some joint work with Hugh Thomas, where we give a q-analogue of a classical story in combinatorics. So let me explain the classical story first. So it's going to involve Schur functions. So what are Schur functions? These are functions indexed by partitions lambda. So what is a partition? A partition is a weakly decreasing sequence of non-negative integers, such as 4, 4, 1. And how we can think of them as also as diagrams of boxes, which are left and top justified, where the entries give the number of boxes in each row. So 4, 4, 1 means we have rows of length 4, 4, and 1. Okay. And what we're going to do is form what are called semistandard tableaux. So this means we're going to fill our boxes with positive integers such that they're weakly increasing from left to right along each row and strictly increasing along each column from top to bottom. Okay. By the way, if there are any questions, please interrupt or raise your take questions. And the Schur function S lambda is the generating function for these semistandard tableaux. So we have our partition lambda. It's a function in infinitely many variables, x sub I for each positive integer I. And what we sum is over these semistandard tableaux of x to the t. So x to the t, what this means is it's the monomial where we multiply x sub I for all i's appearing in this tableau. So for example, for this one, we would get x1 times x3 times x3 times x4 times x4 times x4 times x8 times x8 times x5. And it's not obvious, but it turns out this is symmetric in the x side. So if we swap two of the variables, we get the same function back. So here's an example of a smaller a smaller partition, so the partition 2, 1. So again, that means we have rows of length 2 and 1. And normally we consider these as functions of infinitely many variables x sub I for every positive integer I, but here we'll just restrict the 3 variables x1, x2, x3, which means our tableau only use the numbers 1, 2, and 3. And it turns out there are 8 tableaux, 8 ways to fill this diagram with 1, 2, and 3, which respect these conditions. So weakly increasing along rows, strictly increasing down columns. And this is the function we get. And if you want, you can check in this case that it is a symmetric function. Okay. So just for motivation, let me mention some of the many places these Schur functions appear. These are some of what I think are personally interesting. So first of all, they form a basis for the algebra of symmetric functions. In fact, an orthonormal basis. So it turns out there's a natural inner product on the space of symmetric functions, and these Schur functions are orthonormal bases. There are also characters for the irreducible polynomial representations of GLNC, the group of n by n invertible matrices over the complex numbers. They're also intimately related to the representation theory of the symmetric group, Sn, of all permutations of n letters. They're also related to the cohomology of Grassmannians. And the one that's going to be most relevant for this talk, though probably the least well-known to combinatorialists, is they're related to Schur processes introduced by Kunkov and Reshetti. So these are certain determinantal point processes where the probabilities involved are defined using Schur functions. Okay, so what we're going to be mainly concerned with is this identity called the Cauchy identity. Though, as often happens in math, this was not actually proved by Cauchy. What Cauchy proved was an identity about determinants, and there's a different definition of the Schur functions in terms of determinants, and you can show that it's equivalent to what Cauchy proved. In any case, we're going to try to understand this identity. So first of all, some motivation. So there's a couple of ways we can think about this identity. One is it's actually equivalent to these Schur functions being an orthonormal basis. The other is it's related to these Schur processes, and it basically gives a partition function for the Schur processes. So in other words, when we assign these probabilities, we need all the probabilities to add up to 1, which means we need to divide by the sum of the probabilities, which turns out to be this sum. Okay, so we're going to try to understand this identity combinatorially, which means we're going to try to expand both sides as a sum of monomials in these variables. So here we have two sets of variables. We have these x variables, x sub I, and the y variables, y sub j. And we want to expand everything in terms of monomials in the xi's and the yj's. And it turns out that on the left-hand side, what we get is terms indexed by non-negative integer matrices. So what's going on is each of these geometric series, we can expand as a geometric series in the variable xi, yj. And the power we take in that geometric series is the entry we put in the row I, column j position of the matrix. So for example, here is an example of a non-negative integer matrix. Really, we should think that this is an infinite matrix extending in both directions, but all the other entries in that infinite matrix would be 0. So we just consider this finite portion where some of the entries are not 0. What about the right-hand side? Well, we have this combinatorial definition of Schur functions as a generating function for semistandard tableaux. And so we can expand each of these Schur functions over semistandard tableau, and what we get is a sum over pairs of tableaux of the same shape, because we're always multiplying an S lambda with an S lambda. So for example, if we take the coefficient of x1, x2, y1, y2 on each side, we get the equality 2 equals 2. And on the left-hand side, we have these two non-negative integer matrices. On the right-hand side, these two pairs of tableaux. And the x and y terms here put constraints on which objects can appear. So for the matrices, the xi's and the yj's, well, the x variables tell us the row sums. So it's telling us the sum of the first row and the second row should each be 1. And the y's tell us the column sums. So the column sums should both be 1 as well. So in fact, that condition actually means that the first two rows and the first two columns, we have a 1, exactly 1, 1 in every row and column. So actually we're getting what are called permutation matrices, which we can just think of as regular permutations of the integers 1 through n. Here n equals 2, so we have the integers 1 and 2. And on the right-hand side, the x variables tell us the entries used in the first tableau, and the y variables tell us the entries used in the second tableau. So in this case, first tableau has a 1 and a 2, and the second tableau has a 1 and a 2. And so there's two pairs of tableau that we can form which have the same shape. So what we're going to want to do is give a bijective proof. So we want to find a bijection between these non-negative integer matrices on the left-hand side and these pairs of tableau on the right-hand side. In this case, here's what we can do. But we wanted something that works in general for an arbitrary monomial. So for the purposes of this talk, I'm going to focus on monomials like this one, which are of the form x1 times x2 through xn times y1, y2 through yn. And in that case, what we get are permutations of n elements on the left-hand side. And on the right-hand side, we get pairs of what are called standard tableaux, which means they use the integers 1 through n, each exactly once. But everything I'm going to say holds for general monomials. Okay. And by the way, in these Schur processes, such a bijective proof actually gives a way to do random sampling for these Schur processes. So it's actually of interest. Okay, so there's a well-known way bijection for this, which is called the Robinson-Shenstedt-Knuth, or RSK correspondence. We're going to use a variation called the Burge correspondence, which is also known as column RSK. So if you've seen RSK before, this is basically RSK, but we use columns instead of rows. If you haven't seen it before, I'll try to explain how it works. So it takes a non-negative integer matrix and it outputs a pair of tableaux of the same shape, P and Q. So let's see what it is in an example. So again, we're working with permutation matrices or just permutations. So here I have my permutation 2, 5, 1, 4, 3. And first, let's calculate the P tableau, which we get by insertion. So I'm going to insert the numbers 2, 5, 1, 4, 3 in order to get a tableau. So first I insert 2. Okay, now I'm going to insert the next number 5 into the first column. And I get this tableau. Now I'm going to insert 1 into the first column. And remember, we have this condition, this semistandard condition, that the entries down each column are supposed to be strictly increasing. So to respect that condition, this 1 is going to replace the 2, and the 2 gets bumped into the next column. Okay, now I'm going to insert the 4. Again, I need to respect this condition, and it looks like the 4, we have a choice. The 4 could bump the 1, or it could bump the 5. But actually, we needed to bump the 5. So what happens is the 4 bumps the 1, then we're going to have a problem in the first row, which we also need to be weakly increasing. So that's why the 4 can't bump the 1, it has to bump the 5. In general, we place the number we're inserting as far down as possible. into the column. So the 4 bumps the 5 and the 5 goes into the second column at the bottom. Okay, now we insert 3, the 3 bumps the 4, the 4 bumps the 5, and the 5 goes into the third column. That's P. What about Q? Q is the recording tableau, which records the new box we added at every step. So here's the first box we added, so I put a 1 in that position. This is the second box we added, so we put a 2 in that position. This is the third box we add, so we put a 3 here, and so on, a 4 and a 5. Okay. So now what I want to explain is a seemingly different, but in fact equivalent way to calculate this bijection using linear algebra. So we're going to look at nilpotent matrices. So what are these? These are square n by n matrices n over some field k, where some power of the matrix is a 0 matrix. An equivalent condition is that all the eigenvalues of n over an algebraic closure of our field are 0. So that means we can put our matrix into Jordan form, where all the eigenvalues, the diagonal entries, are 0. And then we can have some combinatorial data we can record from these Jordan forms, which are the sizes of the Jordan blocks. And we're going to form a partition, which we call the transpose Jordan form partition, where the column lengths are the sizes of the Jordan blocks. So that's why we call it the transpose partition, because the sizes are the column lengths rather than the row lengths. So for example, here we have a nilpotent Jordan block, which is of size 3. And we associate to it the partition, which has a column of length 3. And here we have Jordan blocks of sizes 2 and 1, and we have columns of length 2 and 1. And here we have 3 Jordan blocks of size 1, and we have 3 columns of length 1. Okay, just to mention, we don't actually have to calculate the Jordan form to find this partition. This formula here, it says that the partition records precisely the data of the dimension, the ranks of all the powers of n. Okay, and here I have some theorem due to Gantzner, which tells us how we can calculate this Burge correspondence using linear algebra, but I'll just try to explain the statement through an example. So let's use the same permutation from before, 2, 5, 1, 4, 3. And we're going to form a nilpotent matrix n. So first of all, it's going to be strictly upper triangular. So it's going to have zeros on and below the diagonal, which automatically implies it's nilpotent. We're also going to set some entries above the diagonal to 0, which correspond to inversions of the permutation, or more precisely, inversions of the inverse of W, which means we basically look for pairs of numbers that are out of order. So for example, let's say 5 and 3 are out of order because 5 is a larger number than 3, but 5 comes before 3 in the permutation. So I look at the 3, 5 entry in row 3 and column 5 here, and I set it to 0. The other entries that I didn't set to 0, I'm going to let be, arbitrary variables, here A, B, C, D, E, and in fact, I want them to be generic elements of my field, which means they should satisfy no non-trivial algebraic relations. And to find the P tableau, we're going to look at a sequence of submatrices. These are the top left submatrices of n. And each of them is also strictly upper triangular, so they're all nilpotent. So they all have some transposed Jordan form partition. I just have to take my word that these are the correct partitions. And then we associate a tableau as before by recording the new box we added at every step. So here's the first box. So we put a 1 here. We have the second box, or this is the second box here. So we put a 2 here. The third box here, so we put a 3 here, and so on. What about Q? Q we get from an analogous procedure using a different sequence of submatrices. So rather than using the top left submatrices, we use the submatrices whose rows and columns are indexed by the first several values of the permutation. So for example, this 3 by 3 submatrix here, I look at the first three values of W, which are 2, 5, and 1. And I take the submatrix whose rows and columns are indexed by 2, 5, and 1. It turns out that these submatrices are also strictly upper triangular. And that's precisely because of these red entries we set to 0 above the diagonal of n. And so we also get a sequence of Jordan form partitions, which we can turn into a tableau, again, by recording which new box we add at every step. Okay, and again, it's not at all obvious, but in general, this gives us the same P and Q tableau as we got from the insertion algorithm. Okay, now what I want to present is a different, a bit more abstract way to phrase this algorithm using flags. So what is a flag? We're going to consider an n-dimensional vector space over a field k to the n. And a complete flag in this vector space is just a sequence of subspaces, f sub I, where we have an f sub I of dimension I for every possible dimension. And each subspace is contained in the next. So we have a 0-dimensional subspace contained in a 1-dimensional subspace, contained in a 2-dimensional subspace, and so on. And we're going to say a nilpotent matrix big N is strictly compatible with our flag if big N sends the I-dimensional subspace inside the I-1 dimensional subspace. I mean, and this condition actually implies that the matrix is nilpotent, because starting from any vector in k to the n, if I apply big N enough times, I'll get sent down to 0. Okay, so if you remember this matrix big N from the previous slide, there's actually a nice way to phrase it in terms of this compatibility condition. So first of all, N we require to be strictly upper triangular, and that means that N is strictly compatible with this flag F called the standard flag. And in the standard flag, the I-dimensional subspace is just spanned by the first I unit vectors. And then we also had these red entries above the diagonal that we set to 0. And that corresponds in addition to requiring N being strictly compatible with F prime, which is the W permuted version of the standard flag. So the J-dimensional subspace is spanned by the unit vectors for the first J values of the permutation. And then we also had this sequence of submatrices, 2 of them, and they're given precisely by restricting, the first sequence is given by restricting N to the subspaces in the first flag, and the second sequence is given by N restricting N to this subspaces in the second flag. And this condition implies that this restriction is well defined. Okay, so one thing this does for us is it allows us to phrase this theorem a bit more generally. We don't have to take these 2 particular flags, F and F prime. We can take any pair of flags, F and F prime, with the correct relative position. So what is relative position? Well, I'm not going to define it, but I'll try to explain some of its properties. So if I have any pair of flags, F and F prime, it has some relative position W, which we write like this, F arrow F prime with W above the arrow. And the relative position is some permutation. And the data it records is precisely all the dimensions when we intersect a subspace in the first flag with a subspace in the second flag. Alternatively, if you've heard of the Schubert decomposition of a flag variety, this permutation W indexes the Schubert cell of the second flag in a Schubert decomposition centered at the first flag. And so this theorem of Gantzner from before, we can state as follows. We take any pair of flags F and F prime with relative position W. we let n be a generic nilpotent matrix, which is strictly compatible with both flags. Then to get P, the P tableau, we restrict n to every subspace in the first flag. This gives a sequence of transposed Jordan form partitions. And by recording the new box at every step, we get a tableau. And this tableau, the notation I'm going to use is JF transpose NF. And to get Q, we do the same thing with F replaced by F prime. So a couple of nice things about this is, first of all, it implies the symmetry of this Burge correspondence. So there's a well-known symmetry property that if we invert our permutation, this swaps the P and the Q tableau. And this is kind of opaque from the insertion definition, but here it's kind of immediate because for relative position, if I switch the two flags, that inverts the permutation in the indexing the relative position. And it also allows us to generalize this theorem kind of in a natural way to the general case. So remember, we want to just not do permutation matrices. We want to work with arbitrary non-negative integer matrices. And to do that, we can use this formulation where instead of having complete flags, we have partial flags. So what a partial flag is rather than having a subspace of every dimension, we might skip some dimensions. So we might have a 0-dimensional subspace inside a 5-dimensional subspace, inside a 9-dimensional subspace, inside a 14-dimensional subspace, for example. And for these partial flags, we still have a notion of relative position, which is now in general a non-negative integer matrix M. But we can still do the same thing as before. We take a generic nilpotent matrix, strictly compatible with both flags, and this gives us two tableaux. And just to mention the history of this, so for permutations, this was discovered in an equivalent version by Gansner, as I mentioned. It was independently discovered in this flag language by Steinberg and Spaltenstein. The general version for not just permutations, but non-negative integer matrices was only proven recently by Rosso about 10 years ago. Okay, so this is the...
When you say partial flag, does that mean that at each step in the flag, does it have to increase or is it weakly increasing?
Yeah, you could repeat a dimension,
Okay.
but then that would just require you to repeat the same subspace again.
Okay.
Because they have to be contained in each other. So yeah, we do allow stuff to be repeated, but that kind of doesn't add anything interesting to the combinatorics or the geometry. Yeah, good question. Okay, so this is the classical story, and now I'm going to discuss a generalization, and one way to motivate it. So this isn't how we started on this project, but what we were doing is we were considering a generic nilpotent matrix, but rather than considering a generic matrix, let's try to enumerate all the possible matrices. So let's work over a finite field. So there's only finitely many objects floating around, and let's try to enumerate all the pairs of tableaux we could get if we consider all possible matrices. And it turns out that things work out very nicely when we do this. So now I'm going to discuss is a q-analogue, which means we're going to throw in a q to everything. And if we set q equals 0, we'll recover the story we had before. So first off, we have a q-analogue of the number n, which is the sum of the first n powers of q. We have the q-analogue of n factorial, which is the product of the q-analogues of the first n positive integers. And we also have this q-analogue of the Schur function called the q-Whittaker function. This q-Whittaker function is also a generating function for a semistandard tableau of shape lambda. The difference is that before, we were summing the monomials x to the t with coefficient 1. Now we have a coefficient which is some function of q. And if we set q to 0, this coefficient becomes 1, and we obtain the Schur function. the name, where does the name q-Whittaker come from? Well, there are these objects called Whittaker functions in representation theory. And if you take a certain limit as q goes to 1, we get Whittaker functions for the Lie algebra GLM. So that's where the name comes from, though in our work, these Whittaker functions don't play a role. We're just going to use this combinatorial definition. So I'm not going to define what this q-weight is in general, but let me try to explain how you get it, at least for a standard tableau in this example. So here we have a standard tableau. It uses the integers 1 through 7 each exactly once. And this is its q-weight. So what we do to calculate it is we imagine building up this tableau by adding the numbers 1 to 7 one at a time. And we're going to look at the row we're adding to. We'll look at its length, subtract the length of the next row, and q-ify it. So, okay, so first we add 1. That's not very interesting. Okay, now let's add 2. The length of this row is 2, and the length of the next row is 0. And 2 minus 0 is 2. Okay, now we add 3. The length of this row is 1. The length of the next row is 0. And 1 minus 0 is 1. Now we add 4. The length of this row is 3. The length of the next row is 1. And 3 minus 1 is 2. And so on. 2 minus 0 is 2. 1 minus 0 is 1. And 3 minus 1 is 2. And we multiply all these together and we get our q. And you can see if I set q equals 0, I get 1 back. And let me also mention, so for experts who know about Macdonald polynomials, these are also specializations of both the p lambda and the h tilde lambda Macdonald polynomials. Okay, so we also have a q-analogue of the Cauchy identity. So it looks more complicated, but it turns out to have similar combinatorics as before. And also it has, again, a similar interpretation. We can interpret this as saying that these q-Whittaker functions form an orthonormal basis for a certain inner product. We can also interpret it as a partition function for q-Whittaker processes. And these are generalizations of Schur processes, which are special cases of Macdonald processes introduced by Borodin and Corwin for the more general Macdonald polynomials. And so these were introduced about 10 years ago, and these Macdonald processes have attracted a lot of attention in this subfield of probability. And that was our motivation for working on this stuff. We were trying to understand some work about q-Whittaker processes from a more concrete point of view. I'll say a bit more about that later. Okay, but as I mentioned, it has similar combinatorics as before. It turns out we can expand the left-hand side as a sum over non-negative integer matrices, the right-hand side as a sum over pairs of semistandard tableaux of the same shape. The only difference is that before, we had like 1 plus 1 equals 1 plus 1. Rather than everything being 1, everything is some function of q. So here we have this non-trivial identity in q. And again, if we set q equals 0, we get 2 equals 2, like before. But we'd still like to have a bijective proof of this identity. Now, unfortunately, there is no bijective proof because, well, I mean, there are 2 terms on each side, but the functions of q are different. Like there's no way to match up the functions of q on the left-hand side and those on the right-hand side. But what we can do is do something more general than a bijection called a probabilistic bijection, which means rather than sending each object on the left-hand side to a unique thing on the right-hand side, we send it to a random thing on the right-hand side. So for example, this permutation 1, 2, we're going to send it to this pair of tableaux with probability 1 minus q, and we're going to send it to this pair of tableaux with probability q. And this permutation, we're just going to send to this pair of tableaux with probability 1. Okay, and then what's supposed to happen is that like this permutation is going to divvy up its q weight according to these probabilities. So this q weight here is supposed to equal this q weight times 1 minus q. And this q weight here is supposed to equal this q weight times q plus this q weight times 1. And it turns out you can check that that's the case. And this still gives, it gives a proof of this identity, which is, in our opinion, as combinatorial as one could hope for. So how do we define these probabilities? Let me explain how we get these probabilities, 1 minus q, q, and 1 in this example. And it's going to be very similar to what we did before. So first, let's start with the permutation 1, 2. We're going to form a strictly upper triangular matrix. And 1 and 2 are in order here. So I don't set this entry to 0. This is going to be some variable, a. And the difference is that before, a was a generic element of some field. Now we're going to take our field to be a finite field of size 1 over q. And a is an arbitrary element. So the intuition is that q is some probabilistic parameter between 0 and 1. And we want 1 over q to be a prime power so that we have a finite field with 1 over q elements. Okay, so we have these two sequences of submatrices from before. But now the tableaux we get are going to depend on the value of a. So if a is non-zero, this matrix, its Jordan form, is going to have one block of size 2. So we get this partition. If a is equal to 0, then we get the 0 matrix, and we have 2 Jordan blocks of size 1. So we get this partition. And q, we get the same thing. So now I want to calculate the probability of each of these things happening. And to do that, I'm just going to say a is a uniformly random element of this finite field. So it's equally likely to be any element of the field. And so what's the probability a is equal to 0? Well, it's just 1 over the size of the field. And the size of the field is 1 over q, so the probability we get is q. And the probability that a is non-zero is 1 minus that. So that's why we get q and 1 minus q on the previous slide. What about the other permutation 2, 1? Well, now 2 and 1 are out of order, so I have to set this entry to 0 above the diagonal. And so there's no randomness. In this case, like with probability 1, we get this pair of tableaux. So that's why we have the probability 1 on the previous slide. So one of our main theorems is that this works in general. So what do I mean by this? Well, we have the same setup as before. We have 2 partial flags, f and f prime, with the correct relative position m. And now we're going to work over the finite field of size 1 over q. And we're going to take a uniformly random nilpotent matrix n, strictly compatible with both flags. And then if I look at the 2 tableaux I get, it's going to depend on the choice of n. So this is going to give me some probability distribution on pairs of semistandard tableaux of the same shape. And these probabilities are going to define my probabilistic bijection. So just like what happened on the previous slide. So let me make several comments. So one comment is, if we set q equals 0, then we're supposed to get what we had before. I can't literally set q equals 0 here, but what we can do is take a limit as q goes to 0. So as q goes to 0, our finite field becomes bigger and bigger. And what happens is, with probability approaching 1, this uniformly random n actually is generic. So we get the generic behavior with probability 1 in the limit. Another comment, so just as every bijection has an inverse bijection, these probabilistic bijections also have an inverse bijection. So in other words, there's also an inverse probabilistic bijection from the other way, where we take a pair of tableaux and we map it to a random non-negative integer matrix. And these probabilities are actually given by exactly the same formula But in this formula, we were fixing f and f prime, and n was uniformly random. To get the probabilities in the other direction, we fix n, and then we take f and f prime to be uniformly random. And the distribution we get on the relative position gives us the inverse probabilistic bijection. And kind of an important thing that we weren't able to prove and we'd like to know is the following: whether these probabilities are rational functions of Q. What we know is if they are rational functions, they're polynomials. So for example, on the previous slide, our probabilities were 1 minus q, q, and 1, which are all polynomials of Q. But in general, we don't know they are. In principle, they could depend somehow on the number theoretic properties of this prime power Q. Like, whether it's congruent to 1 modulo something or not. So we'd like to know whether that happens or not. And in fact, more so, we'd like some combinatorial interpretation of these probabilities, such as a recursive formula that we could use to calculate them and also show their polynomial. And another comment, so this is actually not the first probabilistic bijection used to prove this identity. In fact, 2 probabilistic bijections were given by Matveyev and Petrov. And how they defined their probabilistic bijections was finding q-analogues of this insertion procedure that I described at the beginning of the talk. And this was actually our motivation for working on this. We were trying to better understand this work of Matveyev and Petrov. And what we discovered is that actually, while we didn't, understand what they did any better, we just found a different probabilistic bijection. So part of the story here is that for these classical like Burge and RSK correspondences, there are various equivalent ways to define them. But for these q-analogues, they actually become different. So the q-analogue of insertion is different from this q-analogue using nilpotent matrices. And one reason that our thing is different is that it's not given by local rules. So there are things called growth diagrams for insertion, which tell us that there are some local rules we can use to do this insertion algorithm. And Matveyev and Petrov's q-analogue is also local in the sense of having local growth rules, but our thing does not have local growth rules. So that's related to this problem. If we did have local growth rules, this would give us a recursion to calculate these probabilities, but we don't have that. Okay, and just a small comment about the proof. How do we prove this? Well, it's some double counting argument. Okay. In the rest of my talk, what I want to discuss is an application of this stuff to representation theory of quivers. So if you don't know anything about this, I'm going to try to give a very quick crash course. So what is a quiver? A quiver is just a directed graph. Here, we're going to use a very simple directed graph, which is a path. And we choose one vertex and color it red, call this sync, and we orient all the edges towards the red vertex. A representation of a quiver is just a way to put a vector space at every vertex and a linear map for every arrow. So for example, here we have a matrix, which is supposed to be a linear map from this vector space to this vector space. Okay, it turns out that there's a nice way to classify these representations up to isomorphism. And we're going to focus on representations in which all these linear maps are injective. And it turns out that the isomorphism class of this family of representations are indexed by non-negative integer matrices. So stuff we've seen before. Okay, now we're going to soup up our representations with additional data. So in addition to having a linear map for the forward of every arrow, we're also going to have a linear map for the reverse of every arrow. But we're going to want some relations to hold at every vertex. So at every vertex, I'm going to look at all the ways that I could leave and come back in 2 steps. And so, for example, if I follow beta and then delta, I get back to where I started. In terms of linear maps, this gives us a linear map starting and ending at this vertex by first applying beta and then applying delta. And I want the sum of all these linear maps at this vertex to equal 0. Up to there's some sign convention, which I won't get into. And there's a fancy name for this, which is called a module over the preprojective algebra. So up to isomorphism, each of these modules over the preprojective algebra is given by some data we've seen before, a pair of partial flags and a nilpotent matrix. So here's our quiver. The black arrows are the forward arrows. So to the left of the red vertex, the subspaces are the subspaces in F. To the right of the red vertex, the subspaces are the subspaces in the second flag F prime. The forward arrows are all identity maps, just the inclusion of one subspace in a flag into a bigger subspace in the same flag. And the reverse arrows in blue are all N, or negative N, according to the sign conventions. Okay. So there's one more piece we need to include, which is the pair of semistandard tableaux. And this comes from something called the Sockle filtration. Let me try to explain what the Sockle filtration is in this example. So what the Sockle filtration does is it records how many arrows we have to apply to send a vector to 0. So here's the first piece of the Sockle filtration, which is called the Sockle. And I'm only recording stuff up to dimension. So this means I have a 0-dimensional space here, a 2-dimensional space here, and a 0-dimensional space here. And what I'm looking at is everything that gets sent to 0 after applying any one arrow. So if I start at this subspace, the span of the first unit vector, then I can apply this black arrow, which is an identity. So this identity, it only sends the 0 vector to 0. So the dimension of that is 0. Similarly, at this subspace, the dimension is 0. What about at this red vertex? Well, there's 2 arrows I can apply. I can either apply this blue arrow or this blue arrow, but both of them send the span of the first 2 unit vectors to 0. So we have a 2-dimensional subspace worth of stuff that gets sent to 0. That's why we have a 2 there. Okay, and then we keep going, and at each step we record the dimension of the new stuff that gets sent to 0 after applying an additional arrow. So for this second row here, I'm looking at stuff that gets sent to 0 after applying any 2 arrows. So for example, starting here, I can apply this arrow, but then I can apply this arrow or this arrow, and both of these blue arrows send E1 to 0. So we have a 1 dimension's worth of stuff, which gets sent to 0. Again, 1 dimension's worth of stuff here. It turns out at the red vertex, nothing new gets sent to 0. So I have dimension 0's worth of new stuff. And then, and the third step, the remaining 1 dimension's worth of stuff at the red vertex gets sent to 0. So you can check that if I start here and apply any 3 arrows, like 1, 2, 3, or 1, or like 1, 2, 3, that everything goes to 0. So because 2 dimensions worth of stuff already went to 0, I put a 1 here, and then everything would be 0 above that. So this gives us some grid of numbers. There are some trivial zeros which are always there. So if we delete these zeros, we get some array of numbers, which is called a reverse plane partition. It basically means that numbers are increasing diagonally this way and diagonally this way. If we split this reverse plane partition in half and rotate each of these pieces, we get what's called a Gelfand-Settlin pattern. And we can translate Gelfand-Settlin patterns into semi-standard tableaux. So I won't explain all the steps that went into that, but suffice it to say there's a standard way to turn some grid of numbers like this into a pair of semi-standard tableaux. And the claim is this pair of semi-standard tableaux is precisely the pair of semi-standard tableaux we get from this data, like we did before. So what's the upshot of this? There's a couple of things. So one is that it allows us to prove enumerative statements about these modules over the preprojective algebra. And it turns out the right way to do this enumeration is we enumerate isomorphism classes of these modules. And we count each isomorphism class according to 1 over the size of its automorphism. And so then we do this enumeration and we can refine it according to the isomorphism class and also the Sockle filtration. So we get enumerative results like this. And the other interesting thing is that, as I mentioned, here we're working with a very special quiver, which is a path with one red vertex. And so in this area of representation theory, like there's stuff known about other quivers. So you could ask for other quivers, such as a Deakin quiver with a minuscule vertex. Is there a version of this story? Is there some tableau combinatorics which gives you the right stuff for that quiver? So that's something we're interested in looking at. All right. Thanks very much.
Questions for Stephen? I have a question, and I don't know if it's correct question, but anyway, okay. So you have these uniformly random, nilpotent matrices in the background. Is there any way to have something that's not uniform?
Yeah, I mean, you certainly could consider something that's not uniform, but yeah, we don't know of any like a way to get something interesting or nice from something that's not uniform. But that's certainly that certainly could be something
I was wondering.
that could be something interesting.
Any other questions? I love this probabilistic q-analogues. It's really cool.
Yeah.
So how did the inverse actually work? I mean, because sometimes you're mapping things to probability, but it was like Q going here, but one of them got more stuff than the other one. Probabilistic.
Right.
So
Oh, I see what you're saying. Yeah, that's just allowed to happen.
yeah, I mean,
So you're defining like a notion of a probabilistic mapping from one thing to another, and saying it's a bijection and like the coefficients line up the way you should.
Yeah. I mean, there are some. Yeah, I guess it's not obvious. Like, what are the axioms they should satisfy? But yeah, there are some, like a few simple axioms.
Plus you have a natural way to come up with these probabilities. That's the whole point. It's not like you just said, oh, this just kind of works. You have a way to get at these probabilities.
Yeah.
That comes out. Oh, very nice. Any other questions or comments or open problems?
Are there other places probabilistic bijections come up, or is that something that y'all do?
So this kind of like this work I mentioned of Matveev and Petrov, just kind of originated in their area of probability. I think it first appeared in work of Upitov and Petrov. So yeah, these are all like probabilists working on these McDonald processes. But yeah, I think like I haven't seen these probabilistic bijections appear elsewhere in combinatorics, but I think they certainly could. I mean, I haven't gone out looking for problems, but it seems like they should appear naturally elsewhere.
Any other comments? Okay, if not, let's thank Steve again. So we are going out to dinner tonight. We have no idea where. You are all welcome to join us. Again, we will pay, so keep that in mind if you get hungry. Okay, thanks again. Let me stop this. Good talk. Super interesting.
Oh, thanks.
Are you done off of safe enough? That's. It'll be wild if you might stay in your car. And like they bringing your air filter and you.
Let me make sure that this meeting is done.
I'm sure it does.
So did you mean the meeting?
Yeah,
Okay.
I'm not even sure the Zoom meeting is finished.
Oh, yeah.
'Cause I started over there. Yeah, it's not done.
Or should I
Yeah, we have to get the meeting.
check this out?